Hello and welcome to our geodetic tutorial. My name is Janine Hilden. I'm an application engineer at Math2Market, and in the following video I will show you how to create a digital bimodal cathode. This can easily be done with the Bimodal Cathode GeoApp, which is introduced in GeoDict 2023. This video is the first video in the small series of videos on how to create a battery from bimodal electrodes and run a degradation simulation on it. You can find the GeoApp in GeoDict by selecting GeoApp up here, and then choose Battery, and then Electrode Generation. In the Module section here, the available electrode generation GeoApps can be selected from the pull-down menu. Since we would like to generate a bimodal cathode, we select this app. Let's click Edit to have a look at the parameters. The Bimodal Cathode app is designed to enter exactly the parameters that you get from the battery production. Right below the result file name, we find the domain parameters defining the special dimensions of the resulting cathode structure in GeoDict. Since we plan to use the cathode for the battery degradation simulation in the final video of the series, we must take care of choosing the right domain settings and remember them for the anode creation. For the x direction, we enter 100 voxels, and for the other two directions, we stay with the 200 voxels. A voxel length of 0.4 is a representative value to potential scans of electrodes or corresponding digital twins. So we can just keep it. The app allows the input of two different active materials. We will use this option to generate two different particle size distributions for the same active material, NMC. For the particle type 1, we stay with the default size distribution. The particle size distribution is defined in d values, meaning that for our structure 10% of the particles will have a diameter of 3 micrometer or lower, and 90% will have a diameter of 10 micrometer or lower, while no particle is smaller than 2 micrometer or larger than 12 micrometer. We also want to define a second particle size distribution, so select Yes here. First, we can define the ratio of particle type 2. Note that this ratio is given in mass percent. In GeoDict it is usually more common to use the volume percentage, but since you get mass percentage values from the laboratory for your electrodes, it is much easier to just enter them directly in GeoDict. Then, of course, you must know the correct density value and provide it with your material in the GeoDict material database. For the materials already defined in the database, like our NMC 333 here, we of course have all the relevant parameters. The d values differ from the values for particle type 1, resulting in NMC particles following two different particle size distributions. Here, we can select materials from the material database for the electrolyte and the carbon binder domain, so all constituent materials of the final cathode can be defined. The CVD amount again is given in mass percent. Finally, we define the criteria to match with our cathode. With these criteria, we can follow a given recipe that we got from the battery development engineers. This way, a certain porosity can be achieved within the small deviation range given by tolerance. With these values here, the algorithm in the GeoApp will try to achieve a porosity around 30% with not more than 3% deviation. Therefore, we can also define the maximum number of tries. So with these settings, the app will iterate twice to try to reach the given criteria to match. Instead of matching the electrode for a specific porosity, we can also select by loading and define the area capacity. So which amount of loading should be achieved for the electrode, again within a given tolerance and the number of tries. We keep the tolerance at 3%. If the desired criteria cannot be matched within a reasonable number of tries and tolerance, you can try to enter different random seeds manually. Note that the maximum number of tries is set 1 automatically. Using the same random seed produces the exactly same structure. Not using a manual random seed will always produce different structures, but following the same statistical properties. Then, we could also apply specific stopping criteria, providing you the chance of a better outcome. For example, if we have a certain target value for the particle overlap to reach, we can enter it here. Additionally, we can define the number of maximum iterations, or time, until the target overlap is reached. But we will not use this option. Now we click OK and Run to finally generate our bimodal cathode. Here we can see that the achieved loading is 2.1, which lays within our given tolerance. Then the geodetic result file is opened in the result viewer. Here we again can see that our desired loading is achieved with only 0.01% deviation. And the porosity is almost 30%, and we can also observe the volume percentage values for our two particle types and the carbon binder domain. The volume percentage of the CVD phase is high to reach the given mass percentage. Let's have a look at our cathode in 3D. Here, in my structure, the NMC particles following the first particle size distribution are colored in light gray and the other NMC particles in dark gray. The binder is visualized in red. This is the end of the first video tutorial in this series. I showed you how to create a bimodal cathode in Geodik 2023. In the next video, I will create a bimodal anode. In the last video, I will then build a battery from our two electrodes to perform a charging simulation and use the results to perform a degradation simulation on this battery in Geodict. If you found this tutorial helpful, please check out our Mathematica channel for more Geodict videos. Goodbye!